Hi, I'm Brendan. So, for this first presentation, I'll be sticking fairly close to the book. So in the first section, we'll be discussing Euclidean space, and more specifically, we'll be discussing Euclidean 3 space. So Euclidean 3 space, it's the set of all ordered triples of real numbers. Okay, so for example, a triple, one triple P, a triple P, I'm just going to denote like that, is equal to P1, comma P2, comma P3. That is called a point in a point of R3. Okay, and so we can usually denote that in using a XYZ plane. So, for example, your point could be 110 or something, and we could just denote it like that, 110. Okay, and we could do that for any point we want, so that's just one example. Okay, so the next thing we're going to look at is that it's just a result from linear algebra that R3 is a vector space over R. And I'm not going to go through this in too much detail, but the main thing you need to know is that when we perform addition, so say we have three vectors, P equals P1, P2, P3, 2, comma P3, Q equals Q1, Q2, Q3, comma Q3, and those are both in R3. Then when we add them, we're just going to add them component-wise. So P plus Q, that's equal to P1 plus Q1 plus Q1, P2 plus Q2, 2, and P3 plus Q3. Okay, and if we have a scalar, and we're just going to define some scalar multiplication, and for a scalar A in R, we can say that A times P, that would just be defined, again, component-wise. So we should multiply A times each component. AP1, AP2, AP3. Okay. Okay, and finally, we define 0, which is just 0, 0, 0 as the origin, which is just as you would expect is the origin of R3. Okay. So that we're going to move on to the next definition then. So let x, comma y, and z be real valued functions. And that means that they take that their range is going to be real valued. So be real valued functions on R3. In other words, functions from R3 to R, such that for each point that for each point P defined as usually as P1, P2, P3. We can say that x of P is equal to P1, y of P is equal to P2, and z of P is equal to P3. So that, what in other words, is just extracting the first, second, and third coordinates individually. Okay, and what we need to know is that these are called the x, comma, y, and z they're called the natural coordinate functions of R3. Okay. Coordinate functions. Okay, good enough. So we can also use index notation instead, which is, it doesn't change anything, but it's just a different way of writing it. So we can write x1 equal to x, just replacing x1 by x, and x2 by y, and x3 by z. Okay, that's just index notation instead. And using these natural coordinate functions, we can write P as P1, P2, P3, P2, P3. We can write this as x of P, which would just be the first coordinate, y of P, and z of P. Or if you want, you can write it using the index notation instead, and that doesn't change anything, but it would just look like this instead. Okay. So from here, I'm gonna assume that you're familiar with partial differentiation and just move on to the next definition. So if you're not familiar with it, or if you just need a reminder, a partial derivative just means that you're taking the derivative of a function of multiple variables with respect to one of them. So, definition, we're going to say that a real valued function f on R3 is differentiable or a few equivalent terms. You could say it's infinitely differentiable. You can say it's smooth. And that's the one I generally use when I'm just talking. Or of class C infinity. Or of class C infinity. And this happens when all of its partial derivatives exist and are continuous, provided that all of its and are continuous. Okay. So I'm just going to go ahead and write out a few examples of continuous functions. Example, the first one would just be f is equal to x plus y plus z. And this is just a polynomial of multiple variables, but it's a polynomial, so it will be continuous. So, and we can make this a little bit, we'll make this a little bit more explicit in just a second, but we're going to move on for now. And as another example, g equals x, y, e to the z is also, and is, it's differentiable or smooth. Okay, and the second one, it seems intuitive that this would be true, but we kind of need the next statement for it to really become obvious. Okay, so I'm just going to call this a theorem. So differentiable functions f and g may be added and multiplied to yield functions that are again differentiable and real valued. Okay, and this is done in the following manner. So f plus g of p, where p is just some point, is equal to f of p plus g of p. And of course, we're making the assumption that f and g are differentiable functions. I already wrote that. And fg of p is equal to f of p, g of p. Okay. And the idea is that they're both differentiable. So, as a quick example, so say f is equal to xy and g equals to yz, and our point is equal to 1, 2, 3. So f and g are clearly smooth. G are, and this is because x, y, and z are all individually smooth, and you're just multiplying them together. So by the previous theorem, that's true. And so, and it also because it's just polynomials. So we can write that. F of p plus g of p is equal to 1 times 2 plus 2 times 3. Just substituting in our values of the point. Okay, that's 8. But it doesn't make a difference. We could have just done this in the other order. In other words, added f and g first and then plugged in the point. So, or xy plus yz of p, and that's of course still going to be 8. And the same thing's going to be true for multiplication. So it makes sense why this is true. There's a little bit more to it, I think, though. So I mean, what I want to show is that we want to show that the product of two continuous functions is continuous. So sorry, the product of two differentiable functions is differentiable. Okay. So the one thing we need to remember is the chain rule, and that just says that the partial derivative d dx of fg is equal to df dx times g plus f times dg dx. Okay. And we can also do the same thing for y and z instead, but we're just looking in terms of x right now. So, but this establishes that all derivatives of all orders exist, because we can just keep repeating this formula, and we'll keep getting sums and products of differentiable functions. Yeah. And we can also see that it's continuous because each of these is continuous, and we know that the sum and product of continuous functions is continuous. So I'm just going to go ahead and write this out. So the chain rule establishes that all derivatives, partial derivatives, of all orders exist. Okay, so we can at least find the derivatives, and we also know that they're continuous, since the sum and product of continuous functions is continuous. So this shows that it's true for multiplication. You could do the same thing for addition, but it should be easier for addition, I believe. Well, all I intended to show was for multiplication, and thank you for listening.